For our last topic in Calculus 2, we're going to be working in a different coordinate system. Now, almost everything that we've done up to this point has been in X and Y coordinates. You might see these called Cartesian coordinates or rectangular coordinates. And it's the job of these things to describe points on the plane. So here I've got the XY plane and I've graphed the point 2, 2. But the important thing here is that 2, 2 is a description. It's an address, if you like. It tells us that this point is supposed to be 2 units away from the x-axis and 2 units away from the y-axis. So those would give me my x and my y coordinates. We're going to look at a different way to describe points, and this will let us graph different kinds of functions. So how else could I describe this kind of point? Well, in polar coordinates, there's only really one special point, and that's the origin. So we still have the origin in, well, we have it in X and Y coordinates, we have it in polar coordinates as well. And rather than have X and Y axes, I'm just going to tell you how far away is the point from the origin, just straight line distance. So if I think about this, it's not so bad to calculate, because my rectangular coordinates, my X and Y axes, come at a right angle, then I can draw this right triangle whose legs are exactly the X and Y coordinates. Here, those are both 2. So I can calculate the length of the hypotenuse with the Pythagorean theorem. Here, that's going to be the square root of 2 squared plus 2 squared. So that'll be the square root of 8, like so. So now I know how far away my point is from the origin. But the problem with this is that there's lots of points that are square root of 8 units away from the origin. Why, if I drew a circle with that radius, let's say the radius r equals the square root of 8. Well, here I've got a circle of that radius drawn in green. The point that I care about here in red is that distance away from the origin, but so is every other point on this circle. So I'm going to keep using this letter r for the radius. Right? This is the distance from the point to the origin. But that's not enough information by itself to tell me where this point is going to be. I'd like to know what direction away from the x-axis I'm supposed to be. Direction away from the origin, excuse me. And for that, I need to measure the angle that this ray makes with the positive x-axis. Why the positive x-axis? Well, I'm already used to measuring angles starting at the positive x-axis and working counterclockwise. So I will continue that convention just to make the arithmetic work out in a familiar way. So if I specify both the radius and the angle theta, now I know where my point is going to be. So for this point right here, I can tell, since my x and my y coordinates are the same, then this must be 1/8 of the full circle. So this theta will be pi divided by 4. Now, many graphing calculators do come with a parametric mode. So if I want to look at these coordinates, can I just put in square root of 8 comma pi over 4? Well, no, that's not quite right. I got this purple dot over here. What happened? Well, Desmos thinks that all ordered pairs are x and y. So if I went the other way, how could I figure out what my x and y coordinates are supposed to be? And the trick to this all comes down to trigonometry. So I've got some point that's described either in the polar coordinates r and theta. So my distance to the origin and my angle with the positive x-axis. Or I've got the same point, but described in its x and y coordinates. Distance from the y-axis, distance from the x-axis. But these things together form a right triangle. And I can convert between them using trigonometry. So if I have the x and y coordinates, how can I find r and theta? Well, I already did r. This is going to be the square root of x squared plus y squared. How am I going to find theta? Well, I know that all of the trig functions for this angle theta are defined in terms of the numbers x, y, and r. So if I took the tangent of theta, I'd get opposite over adjacent. This tells me that the tangent of theta equals y divided by x. So does that tell me what theta is? Well, almost. I know that lots of different thetas will have the same tangent value. Theta can repeat, right? Every pi units, I'll get the same value for the tangent function. So one option is that theta equals the arctangent of y divided by x. But I could have wrapped around and gone an extra time around the origin before I stop at the same place. So I could have different angles theta that will describe the same point. This is one of the technicalities in working with polar coordinates, is that it's not a unique description. Same point here in red can have lots of different r's and thetas that tell us where to find that point. Now, what about the other way? How about I know r and theta? How do I get back to my x and y? Well, this version is actually a lot easier. Since I know that sine of theta is opposite over hypotenuse. So how do I get that opposite edge by itself? Y has to be r times the sine of theta. And likewise, x has to be r times the cosine of theta. So if I want to graph this point using the polar coordinates instead, on Desmos, how I'll have to do that is I want this coordinate pair. Desmos thinks this is an x and y. So I'll put in r times the cosine of the angle I want. My r is the square root of 8 times cosine. And the angle that I want was pi over 4. I need parentheses there. Okay, there's my x coordinate. My y coordinate is going to be almost the same radius, the same angle, but now with the sine function instead of the cosine function. So again, here in red was my point 2, 2. And for my polar coordinates is r equals 8, theta equals pi over 4, and I get exactly that same point. And what I was saying earlier, I can add 2 times pi to my angle measure. Both the cosine function and the sine function are periodic, with period equal to pi. So I have lots of different ways of writing the same coordinate. So that is how we can find the addresses for coordinates using the polar system. The reason we call it the polar system is because we can imagine this line, let's say, pointing from the origin to the point that we want. And no matter where in the plane we go, this line segment is going to point back and tell us the distance from the origin. So you can imagine sort of a literal pole sticking up out of the origin, and we're just running around it with this kind of ribbon attached to it. So that's how the system works. But what we want to do is we want to graph curves. We want to have functions. So when we go to graph a single one of these points, we need 2 pieces of information. What direction do we face, and how far do we go? And just like in the Cartesian system, we pick one of these things, and then the other of them is determined by a formula. So when I say y equals x squared, what I'm doing is I'm saying when we have gone 2 units along the x-axis, that was my x movement. Now I need to move in the y direction according to this formula. The square of 2 is 4, so I move up 4 in the y direction. To graph in polar coordinates, we're going to use theta as the independent variable. So we're going to start at the origin, and we're going to pick a direction first. And then depending on what that direction is, the formula for my function will tell me how far to go. So as an example here, let's say r equals just 1. That's easy enough. So this is a function. It is a constant function, so that no matter what direction I choose to walk out in, I start at the origin and I move 1 unit in that direction. So for an angle of 0 radians, I go 1 unit. For an angle of pi on 4 radians, I move 1 unit, and so on. Let's make this more interesting. Let's say I want r equals 1 plus theta. Now I get this spiral. So kind of like with the parametric equations, Desmos has decided that this is going to be graphed for theta between 0 and 12 pi. And as I zoom out, I find that I get this nice spiral pattern. So what's going on? The smallest value of theta that I've got is 0. So I look to the direction described by 0 radians. That's just along the x-axis. And I walk out by 1 plus 0 units. And I get this point right here. So this would be the point just 1, 0. To plot the later points on this curve, I pick a different direction. Maybe theta equals pi over 4. So I'll be going in the positive y direction for pi over 2 is the positive y direction. And I go out a distance of 1 plus pi over 2. And I get to this point right here. And so as I change my direction, I've got longer and longer radii. So I'm describing this spiral like so. Now, something important happens when I get to theta equals 2 times pi. Even though I'm describing the same direction as theta equals 0, right? I've gone once around my spiral. My angle measure really is 2 pi for the fact that I've gone around the origin once. And so my new radius is not 1, it's 1 plus 2 pi. So I go out further than I did before. In fact, for this curve that I've graphed, my radius, my r, is an increasing function of theta. So the more times I twist around the origin, the farther my point is going to be. So the farther out my spiral arm is going to be from the origin. So this fails the vertical line test, but that's not the kind of function that I'm interested in today. I want to know, is this curve represented so that my distance from the origin, my r, is a function of how many times I have twisted around the origin? And for here, the answer is yes. Now, in general, I can graph things that look like r equals f of theta. I just need to describe what that function is. So here again here is a different spiral. R just equals theta. Again, these are very nice coordinate systems for describing spirals. But in general, my functions can be negative, right? Functions can produce any kind of number, positive, 0, negative. So what happens if I have a negative number for my radius? Looks like the spiral flipped around, right? Why is that happening? So I need to explain how the polar coordinate system handles negative radii. So when I pick my angle, let's say my angle is 3 pi divided by 4. And I know that I'm going to be traveling out along this path. Well, even with my angle set here, there's two different directions that I can go and still be on this line. So everything that I've been doing so far is I say that I've got my angle and I start walking out forwards some amount of distance, right? So I could say I'm going out this way, a distance of, say, r equals 10. If I take a smaller r value, I wouldn't go as far, say r equals 5 or r equals 1. R equals 0 would be not moving at all. So that would just be the origin itself right there. And continuing that pattern, if I choose a negative value of r, it's as though I've picked a direction to face in, and now I'm walking backwards. So if I stopped at r equals -1, I wouldn't be going out along the pink ray, I'd be going out along the green, as long as those are showing up as different on your video while you're watching this. So I'd end up about here. If I went, say, I'm facing the angle of 3 pi on 4, and I walk backwards 5 units, I'd end out over here. If I walk backwards 10 units, I might end up back over here, and so on. So when I'm graphing, let's say r equals f of theta. F of theta is just theta. Let's look at this graph again. Let's have positive and negative values of theta, though. Let's say we go from -pi up to pi. I get this strange looping shape. Why is that? So I start at the origin. My smallest angle measure is -pi. And I'm supposed to be traveling a negative distance. So I'm facing this direction to the left here, and I walk backwards from the origin until I get to this point here. So as I go, right, I'm facing this, I'm facing this way, and I am turning to look out at, say, theta equals -pi, theta equals -pi on 2, theta equals 0, theta equals pi on 2, theta equals pi. This arrow here is representing the direction that I face. If I walked backwards from there, I end up over here. And I'm going to follow this path until finally, now I'm facing theta equals 0, and I've gone 0 units. So I'm at the origin itself. And from there, I have positive radii. I have positive distance I'm going to travel away from the origin. And that's how I get this sort of a safety pin kind of looking thing. Now, your homework for right now is just focusing on working with these kinds of curves working with this kind of coordinate system. My next lectures will be on how to do calculus in this setting. So specifically how to do integrals in polar coordinates. There's some technicalities we've got to iron out to make everything work. But we're almost done with the term. After we get through polar integrals, we'll just be into our review session, and then soon enough we'll have wrapped up the term. See ya.